Jet engines don't just push planes forward, they also need to bleed. Sounds ominous? It's actually a brilliant design feature. In this video, we'll explore how bleeding a jet engine helps prevent turbine meltdown, warms the cabin, and even keeps the aircraft safely in the sky. Let's take a closer look inside a modern turbofan engine to see exactly where and why it needs to bleed. As we move closer, notice the shiny metallic intake at the front of the engine. It's intentionally left unpainted for a specific reason, something we'll explore shortly. Here's the engine up close. Observe the four annular rings carefully positioned along the compressor. These are called bleed ports, and they are used to extract high-pressure air. The first two rings near the front are primarily for anti-stall protection. By bleeding a small amount of air, the engine maintains smooth airflow through the compressor and prevents stalls during high power changes or uneven airflow conditions. The two rings toward the rear serve different roles. They provide hot, pressurized air for wing and engine de-icing, so to keep the aircraft safe in icy conditions. Now observe the red-colored ring behind the engine air intake. This is the anti-icing system, fed with hot bleed air. And that shiny metallic rim at the front? It's left unpainted to conduct heat more effectively, thus preventing ice from forming. Next, let's follow the bleed air tubing and see where it leads to. Note that most commercial aircraft still rely on bleed air for anti-icing, a tried and tested method. In the future, we'll likely see more electric heating systems, lighter, more efficient, and precise. But for now, bleed air remains the workhorse of safe flight. Notice how the bleed air is directed. Part flows toward the wing's de-icing, while part goes into the environmental control system, which pressurizes and warms the cabin for passengers and crew. Now let's follow the hot bleed air into the air cycle machine, or ACM. This compact system uses two heat exchangers, HEX1 at the front and HEX2 at the back. First, the hot bleed air enters heat exchanger 1. Here, it cools down significantly, thanks to cold ram air flowing over the exchanger. This initial stage brings the air temperature down, reducing the load on the compressor and downstream components. Next, the air passes through the compressor, driven by the expansion turbine, before moving on to heat exchanger 2. The second heat exchanger further cools the air, bringing it closer to the temperature we need for cabin pressurization and environmental control. So why two stages instead of one? Splitting the cooling into two heat exchangers allows more efficient temperature reduction, reduces thermal stress on components, and ensures the air entering the cabin is at the right temperature and pressure. Now for cooling the heat exchangers, ram air is obtained from outside the aircraft. This passive cooling works in combination with the machine's internal compressor and expansion turbine to achieve precise temperature control. This technique is very efficient, especially at cruising altitudes as outside air is below zero. Now the cooled high-pressure air enters the centrifugal compressor, gets compressed, and then expands through the turbine. This expansion not only drives the compressor but also lowers the air temperature further before it exits to the mixer manifold, ready to be sent into the cabin. This clever combination of staged heat exchangers, ram air cooling, and expansion-driven compression makes the air cycle machine highly efficient, delivering comfortable, pressurized air to the aircraft while using the engine's bleed air effectively. Now inside the mixing manifold, about 70% of the cabin air is recirculated and blended with around 30% of fresh ram air. This mix helps maintain just the right temperature and pressure for everyone on board. Also observe that most airliners have at least two air cycle machines, one powered by each engine. This provides redundancy, so if one engine or pack fails, the other can still keep the cabin comfortable. Also, both systems are linked through what's known as a cross-bleed manifold. This allows hot bleed air from either engine to feed both air cycle machines if needed, ensuring continuous airflow to the cabin, even during single-engine operation or when one pack is offline. Next, let's look at another major use of bleed air. Bleed air also plays a key role in preventing the turbine blades from melting. For instance, the high-pressure turbine operates at temperatures exceeding 1,500 degrees Celsius, where most metal alloys would quickly weaken or even melt. To protect these components, high-pressure bleed air is extracted from the compressor and routed through the orange-colored ducting shown here. This air is then directed into the turbine blades themselves. Each turbine blade and guide vane is hollow inside, allowing this cooling air to flow through internal passages, keeping the metal temperature within safe limits. This cooling method is essential for the reliable and safe operation of modern jet engines. Without this internal cooling, the extreme heat from the combustion gases would destroy the blades in minutes. By using a carefully controlled flow of bleed air, engineers can operate turbines at temperatures far above the metal's melting point, a remarkable example of engineering ingenuity. And that brings us to the end of this presentation. As always, if you enjoyed this video or found the content useful, please remember to like, subscribe, and share your thoughts in the comments below. Thanks for watching, and see you in the next video.